Good afternoon, everyone. Welcome you all here I think it's going to be a wonderful presentation. Simge has done a lot of work in mixed integer optimization and applications, and she's really going to provide a wonderful perspective of how this all fits together, both the theory and the practice. She's not afraid to do her administrative work. She's now chair in her department, so contributing to the health of that department. Also, most recently, her administrative, her scholarship, and her contributions to the society have been recognized as being one of the latest Informs fellows. So congratulate you on that honor. And I'm not going to say too much more, except that your work is just, she presents things in a very understandable way, and we get to kind of see the heart of what's going on. I will also mention to you, and I'm in search of it myself, but also there is an accompanying volume which at least can be ordered from Informs, and I hope there might be some display copies available that go into more of the technical details, give lots of references. But the talks here themselves, I tend to be a wonderful overview of the problem areas and the solution techniques. So without further ado, I will let Simge Kachukevich continue with her presentation.
Thank you, Doug. Thank you for the nice introduction, and thank you all for coming to this tutorial. So yeah, as Doug mentioned, today I'm going to talk about mixed integer programming approaches to what we refer to as generalized submodular optimization and its applications. So this is joint work with Kim Yu, my former PhD student who just graduated, and she's becoming an assistant professor at the University of Montreal. She was supposed to be here to present half of the talk, but there are some visa issues that prevented her from coming. I've also done some work with my former student Hao Xiang Yu on this topic, so I'll present some of that work as well. But the tutorial paper Doug mentioned has been jointly written with Kim, based on her dissertation work. So just an overview of what I'm going to talk about today. So I'm going to introduce, for those of you who may not be familiar, what submodularity is, how we exploit it, especially with mixed integer programming-based methods. Sometimes submodularity will be hidden, so how we uncover it, how we find submodularity when it may not be apparent, and how we exploit it. And then I'll talk about generalizations, some generalizations. I'll talk about it a little bit in this talk, and more details will be in the accompanying paper. And woven through my talk will be applications and computations. So please feel free to stop me, or maybe I'll take the questions at the end if that's easier. All right, so let's start with the definitions of submodularity. What is it? So submodular functions are set functions. They're defined on a ground set, let's say capital N of n items, little n items. Here is the sort of the first definition of set function submodularity. So it's from subsets of n. If you take two subsets, x and y, sum their function values, that's greater or equal to the function value evaluations of the union and intersection added up. So that's one definition of submodularity. What I find more intuitive is the second definition of submodularity. It's defined by the marginals. So rho is, this is a notation I'll use throughout, is the marginal contribution of adding item I from the ground set to the subset S. So by definition, I is not an S. So as you can see, this is the difference between f of s and f of s union I. What is the contribution of adding I to s? That's the marginal. So a second and maybe more intuitive definition of submodularity is this one, where it says you have two subsets, x and y. This time, x is a subset of y. You take an item I that is not in y or x, and the marginal contribution of adding I to that smaller subset x is larger than adding it to the larger subset y. So this is intuitively a diminishing returns property. The larger the set that you have, the less the marginal contribution of adding an item I to that is. So here's a pictorial representation. The color didn't come out nicely, but I have two, let's say, sensors. I'll be talking about sensor location a lot. I have two sensors, 1 and 2, on the left, and 1, 2, and 3 on the right. They have a circular coverage region. I don't know if you can see it. It's in light blue here, and my pointer is also not working well. X is 1 and 2, and Y is 1, 2, and 3. Y is the larger set. And I'm thinking about adding this other item, I, given by the dark shaded region. As you can see, the coverage, additional coverage of adding I to the smaller set is larger than adding it to the larger set. So that's submodularity intuitively in the sensor coverage setting. So sensor placement is one application that this pops up a lot, coverage functions. Facility location is another classical application of submodularity. It comes up in social networks and influence maximization functions. These are submodular functions, coverage functions in a different sense on a graph coverage. And in some portfolio management problems, I'll talk about one application. This also pops up in terms of risk functions, utility functions based on risk. So anytime you hear clustering, coverage, economies of scale, diminishing returns, these might be hints that you're looking at a function that is submodular. And you might, so this is the hidden part. If it's not obvious, this is where you might start digging into whether this function is submodular. So let's start with the easiest case, unconstrained submodular minimization. So we're minimizing a set function, f of s, s subset of n, no constraints on s. You can equivalently write this, and this is the approach I'm going to take throughout my talk. I'm interested in mixed integer programming approaches. So I'm going to try, and this is a set function, but I'm more comfortable with integer variables, continuous variables, and optimization written in terms of such functions. So I'll turn this problem into minimizing w. W is a sort of a placeholder for my objective function. And x and w are in this set qf. And qf is what we refer to as an epigraph of the function f. So w is greater than or equal to f of x. And x translates the set function or the subset that we're selecting into these binary variables. If a variable I belongs to the set S, I'm going to say xi is equal to 1 and xi is equal to 0 otherwise. So I turn this set function, combinatorial set function representation of constraint submodular minimization into a sort of a mixed integer programming representation where I think of the convex hull of these points. So the 0, 1 to the n points, and w, this continuous variable capturing the epigraph of f of x, so you want to be above the function f of x, and we want to take all convex combinations of these feasible points. If I can do this successfully, if I can represent this in linear fashion, then I can solve a linear program instead of solving this combinatorial optimization problem. So that's sort of the holy grail in mixed integer programming. As a sort of class of problems, unconstrained submodular minimization is polytime solvable and actually strongly polynomial time solvable. The convex hull of the epigraph, that QF, actually these are defined by linear inequalities. These are known as extended polymatroid inequalities. So the linear inequalities take this form, W greater than or equal to pi transpose x. Pi's are going to be our constraint coefficients, and this is linear, as you can see. What should pi be? Well, it turns out any pi that is an extreme point of the following feasible set, we call it PF, this is the extended polymatroid, where we're looking at pi's, the coefficients, such that summation of pi's, pi I and s, the selected subset, is less than or equal to the function evaluation at that subset s for all s. If you look at all subsets, if you write these constraints down for all subsets for your feasible pi, any extreme point of this will give you sort of a facet or strongest valid inequality you need, linear inequality you need for the convex hull. Well, this again is not very maybe immediately useful in an algorithm. So how should we find these pi instead of looking at this exponentially sized polyhedron? It turns out again that pi, the extreme points of that extended polymatroid, can be written in closed form in a very easy manner using those marginals that I introduced earlier, the row functions or the row values. So how does this work? How do we find these extreme points that are going to give us the linear inequalities? You determine a permutation, delta 1 through delta n, and you look at nested subsets of this permutation. So start with empty set, then we have row 1, then we have row 1 and row 2, row 1, row 2, row 3, etc. So these nested subsets. And the coefficients that we have for the linear inequality, the pi's that I show you, are nothing but rho of delta I, which I define over here, which is adding rho I to the nested subset from rho 1 to rho I minus 1. So we increment our subsets with these, following this order that is prescribed by delta, and that marginal contribution we add, this item delta I to the set up until delta I, gives us the coefficient of that linear constraint. So it's actually, for every permutation, it's very easy to calculate what you need. Again, we have exponentially many such permutations, but I'll talk about that in a little bit. So simple example, let's just take the natural order, 1 through n. And for a moment, let's assume that we look at a subset S, also following the natural order from 1 to little s. Little s is somewhere less than or equal to n. So when you write down this linear inequality that I showed you, we'll have I goes from 1 to n, rho of delta I of x delta I, where we selected the subset S, xi is 1 if I is in S and 0 otherwise. That means the first S items are going to have a xi of 1. So I'm going to pick up those coefficients rho I, and everything else will be 0, so I'll drop that. And if you look at the marginals, like I said, it's the marginal of adding one element to the nested set up until that element. A lot of things will cancel out, and you'll get that function value. So the inequality is achieving exactly the function value that you need if you take the order to be in this way. Well, this is true for any function, but for this inequality to be valid, it needs to be valid for any other subset that I may select, other than S, for this particular choice of the inequality. And submodularity, the fact that I have diminishing returns, guarantees that this inequality is valid for any other subset also. It provides a valid lower bound. I will not go into the details of that, but it comes from the submodularity property, that this is valid for any other subset as well. So this is a valid inequality. What's more, that these are the only inequalities that you need to define the convex hull of the epigraph of a submodular function, which means you can now rewrite this problem as an exponential size linear program, right? So, well, how do we solve an exponential size linear program? We actually typically use a delayed constraint generation. You cannot enter this exponential LP at once unless you have very small ground sets. But you can actually use delayed constraint generation. You generate a few of these permutations and valid inequalities, maybe none to start with. Get us what we call a relaxed master problem. Get an x bar and w bar. So w bar is an estimate of your objective function value, and x bar is a potentially fractional solution, because we're solving linear programs now. If our estimate of the objective function w bar is less than what it needs to be, then we need to add one of these extended polymatroid inequalities. And that's a problem we call a separation problem. Which inequality are we missing that should have been there and this shouldn't have happened? So we find that and we add that and we repeat this process. Well, so how do we separate? It turns out separating extended polymatroid inequalities is very easy. It's just a sorting algorithm. Sort the x bar to obtain the permutation that you need. And from the polynomial equivalence of optimization and separation, a very, very well-known theorem, use some ellipsoid arguments. This results in a polynomial time algorithm. Even though the number of inequalities is exponential, you can argue that this algorithm is polynomial time solvable. Well, that was the unconstrained case, but oftentimes we are dealing in sensor location and other problems, we're dealing with constraint problems. A very simple constraint like a cardinality constraint, you cannot choose more than k items, makes this problem hard. It's actually NP hard and hard to approximate. But what we can do, and why I'm promoting sort of a mixed integer programming approach, is any constraint, cardinality, or any other more complicated constraints that you might add to this problem. Now we can use these extended polymetric inequalities to capture the nonlinear function, set function, and your set of constraints, ideally linear, that describe the feasible region of how you should choose S. Now we can solve these problems as mixed integer linear programs. So now I have to keep integrality. It's not a linear program anymore. But I can now solve a series of integer programs and find which cuts that I need to add to capture my nonlinear function. And this has been used in some applications like mean risk optimization. And this is the approach that I will follow today and also generalize to other more general submodular functions. So that's the minimization side. On the maximization side, so even the unconstrained maximization, same problem. This time I'm maximizing my objective of a submodular function. I can do a similar transformation. Now, instead of looking at an epigraph, W that is above f of x, I'm looking at what's called as hypograph, so W that is below f of x. So that will be h of f, the convex hull of the hypograph of f. Again, if I can characterize the convex hull, I can solve this as an LP. This is sort of our dream. If that doesn't happen, we're going to solve mixed integer linear programs as long as I can capture that nonlinear function f of x in a nice way. And my hope is to capture it with linear functions. So turn that nonlinear diminishing returns type f of x into a linearly approximated function. Well, again, in 1988, Nemhauser and Woolsey has a proposal. So here's a so-called submodular inequalities. So this is now capturing the hypograph of a submodular function. So this is one class of inequalities that are known to be valid and capture the objective function values, sort of upper bound of objective function value. So what this function says is, again, for every subset S, the valid inequality says W, this objective function variable, is less or equal to the function evaluation at that subset, plus the marginal contribution of adding items J that are currently not in S to S, multiplied by that binary variable, and subtracting from it the marginals of adding items J in S to n set minus J times 1 minus xj. So what this means is removing item j from the subset S. Essentially, how much you take down from the objective function value, and this provides a good, a correct value for you to add to the right-hand side to get the right upper bound. So these are valid inequalities. They do not describe the convex hull because this is an NP hard problem already. Unconstrained maximization, submodular maximization in general is NP hard. But at least, again, now we can talk about a mixed integer linear programming formulation of this nonlinear function maximization f of x. There's a very well-known celebrated approximation algorithm, 1 minus 1 over e, like 63.63 approximation algorithm for cardinality constraints. So just the cardinality constraint, it has some generalizations to knapsack constraints as well, and monotone submodular maximization. And that's also a greedy algorithm. But again, that's an approximation algorithm. We'd like to think about sort of exact methods and integer programming based, exact optimal solutions. So one thing that is sort of fascinating about submodular functions is I told you that unconstrained minimization, so the diminishing returns, so it's like a diminishing returns property, that sounds concave, right? So diminishing returns sounds like a concave function. But I also just told you that unconstrained minimization is easy. Usually we think of minimization of convex functions being easy. So maximization is hard, minimization is easy, so it sort of has this convex type behavior as well. So what I'd like to think about is, so I drew a concave function in one dimension. And remember that x is now binary, whether to select or not. So x is 0 or 1. So I really only care about the function evaluation at x equals 0 or 1, and I'm looking at being above it. In the minimization case, I'm looking at being above it. So this is sort of, in some sense, well-behaved, and we can actually think of this as some sort of a discrete convexity. So not fully satisfactorily answered this dilemma, but in some sense, these are very interesting functions that sometimes behave like concave functions and sometimes behave like convex functions. But in the minimization case, unconstrained case, we can capture that non-convex looking, continuous-wise non-convex looking function to a piecewise linear approximation. So that's about submodularity. A few operations on submodular functions that maintain submodularity that I'll refer to in my talk. So if you add or subtract a constant from a submodular function, that's still submodular, which is why I'm going to, throughout my talk, I'm going to say f of empty set is 0, because I can always subtract if it is non-zero. So if we have multiple submodular functions fi, and you can think of these I as some sort of scenario, some possibility of what your actual function might look like, with probabilities alpha I, let's say. So if I take the expected value in some sense, then that will be a submodular function as well. So any non-negative weight combinations of submodular functions are submodular. Again, so expectation of stochastic submodular functions will be a submodular function as well. And another thing I will talk about in my first part of my talk is f is a concave function and g is a non-negative linear function. So if you take, if you compose f and g, that will be a submodular function as well. So f is concave and g is a non-negative linear combination function of set function. This will be a submodular function as well. So this will be in the first part of my talk, which is what I refer to as concave submodular minimization. So with the preliminaries out of the way, we can talk about this class of problems I'd like to talk about, which is the first class of problems, concave submodular minimization problems. So the facility location problem I referred to, and also this one class of investment portfolio management problems can be modeled as concave submodular functions. So this is going to be the particular form that we're looking at. Ground set n as before, concave function f, and we're going to look at non-negative weights ai for each I in n, and we're looking at f of ai summed up for I in x. So that's the set function we have as capital F of x, and it is composed of this concave function f and the summation of the weights ai I in x for all x. So again, I'd like to think of things in terms of binary variables or integer variables. So I'm going to replace that capital X subset notation with the little x, and I'll be using these interchangeably throughout my talk and in the paper. So xi is 1 if I is in x and 0 otherwise, and we're looking at f of ai xi summed up over all I in n. So how does this appear in portfolio management? This is a very simplified and perhaps unrealistic version, and then I'll come to the more realistic version. We have multiple options for our portfolio to choose from for our financial portfolio in terms of stocks, and we don't want to invest a little bit in many stocks, so we have to keep a sparse portfolio. Say we want to select K options, and so that's the cardinality constraint, and then we're minimizing minimize the total loss plus perceived risk. Here, if you measure the risk, if you ignore correlations and look at sort of the risk, only the variances of the options, which is the part that is unrealistic, but I'll address that later, then this is exactly in the form that I want. It is in a concave composed with a summation of the concave being the square root function, and the variances provide the AIs that I need. And the intuition here is sort of the sort of diversification principle in portfolio management, that if you add, if your portfolio is diversified, adding another stock is going to add less risk than if it is less diversified. So this is one application of diminishing returns as well. So that's an example. I'll refer to that later. Again, this isn't the uncorrelated case, what this would look like. We're minimizing average loss plus the risk. Here it's measured in terms of this standard deviation, so risk aversion parameter omega, square root of A transpose X, so that would be your standard deviation. Cardinality constraint, peak at most K, and AIs are the variances of each stock. This can also be seen as a value at risk minimization. This is a well-known result in portfolio optimization. It's a chance constraint type of problem where you're minimizing the value at risk Z such that the probability that your return is less than or equal to Z is greater than or equal to beta, where beta is this parameter between 0.5 and 1. And mapping it back to the original formulation, gamma will be the inverse of the standard normal CDF taken at this risk level beta. All right, so what can we do about this problem? Again, this is in the vanilla form without additional constraint. This will be a cardinality constraint concave submodular minimization problem in the form that I showed you. And again, we're interested in posing this as a mixed integer linear program. And in the weight function AI, the variances, we're going to also introduce another notation, little m. These are the number of distinct values of the vector A. If each of the variances is a different number, m will be equal to n, but it's going to come back later why I differentiate this case. And k is the cardinality upper bound. Again, we're looking at the epigraph formulation, w greater than or equal to f of a xi summed up, and cardinality constraint. Again, our goal is to find an exact optimal solution to this problem, and the state-of-the-art solvers struggle with generic f. So I didn't necessarily define f. In the portfolio example, this was a square root function, but in general, it could be any concave function. And such a function with binary variables and continuous variables, the state-of-the-art solvers do not necessarily handle these problems well at the moment. Again, our dream result, ideal result will be if we have the convex hull, then it will just be an LP, and it will be exponential, but we can do this delayed cut generation method. But if we can't get the full convex hull, we can at least have some Weld inequalities and now solve the problem with this as a series of mixed integer linear programs. So that's the second best goal. Again, some complexity results about this problem. It turns out that even though this is a cardinality constraint submodular minimization problem, it has this nice structure, concavity. So this particular subclass is polynomial time solvable. So there is some hope for us to get the convex hull result. And why are we interested in the polyhedral description, mixed integer programming description? We want to add more constraints. So if we add more constraints, we lose this sort of polynomial time solvability result, but we can still use mixed integer programming. So we'll be interested in that pkm, the polyhedron that captures the epigraph of this function with m different weights and this a vector. This has been looked at before. So for one weight, every a has the same element, ai equals some constant a. Actually, there is a class of inequalities known as separation inequalities that were shown to give the convex hull. So this is well understood if all weights are equal. There's an algorithm to generate one class of inequalities, not necessarily the convex hull for general number of weights, but again, it's an algorithmic way to generate an inequality, so it doesn't immediately translate to a separation algorithm within a delayed cut generation. So it's been an open problem how to characterize the convex hull for two or more item weights. And so this is how we started. With Kim, we started looking at this problem. So just a quick summary. Again, a lot of the details, technical details will be in the paper, but at a high level, we started with m equals 2. Actually, we looked at general m, and there are some challenges there. So we scaled back to m equals 2. We are able to give strong Weld inequalities for the two distinct weight item case. It's in closed form, so not algorithm, but in closed form way of expressing the coefficients, just like we did with extended polymatroid inequalities. And we can tell when these are the strongest possible, so that's called facet defining in mixed integer programming, so we can give conditions when this is the strongest possible. And if k is also 2, so p2, they are enough to give the convex hull with some easy separation algorithms as well. So how is this useful? This is very limited, m equals 2, k equals 2. Well, we can start with this and generalize these inequalities to pkm. So k, cardinality, and m, a number of distinct weights. And I'm going to talk about our computational experiments with this. So that's the agenda for the next few minutes. Again, so now this is the set we're looking at. Now I'm going to restrict ourselves to, let's say, pk2 for the m equals 2 case. The idea is sort of a technique in mixed integer programming known as lifting. So we start with a base case. So I will select a subset B of items, capital B of items, going from 1 to little b. And I will only restrict ourselves to choose from these subset, this subset B, and look at this restricted set. Then, if you know a Weld inequality for this base case, so we call it a Bayes inequality, so some pi I xi I want to be that is valid for the set. And then we're going to try and introduce the variables that we've been ignoring to this inequality to make it valid. And that's the process called lifting. So we lift this inequality with the variables that we've been ignoring and get coefficients phi j for those variables. So without loss of generality, let's say these are from b plus 1 to n. So that's the goal. What does lifting problem look like? How do we find these phi's? And I want to do this in closed form. I want to get these phi's in closed form. So there are two things to figure out. What's the Bayes inequality to start from? The most obvious one is the extended polymatroid inequalities that I talked about, and also the separation inequalities that were looked at for single weight case, single AI equals to A case. And then how to get phi's, how to get these phi's in closed form in a sort of the strongest possible phi's. So lifting problems are another sort of optimization problems, mixed integer optimization problems. It is written in the form that I give here. I won't go into the details in the interest of time, but it's a mixed integer program. It is sequence dependent. It depends on how you selected your B and how you're going to add the variables one at a time. So this is usually a very daunting task again. You oftentimes can't solve these in closed form and give all the coefficients without fixing the order, etc. So that's the question we had, you know, how are we going to get these coefficients phi in closed form? How can we solve these lifting problems? And it turns out that we can do that. When we start out with extended polymatroid inequalities that I introduced for the regular unconstrained case, we can give closed form coefficients of phi and characterize them easily. These are facet defining, the strongest possible inequalities you can write for the two-weight case. And they're stronger than some of the closed form approximate lifted inequalities proposed earlier, which are in closed form. So already we can get something stronger starting from the very base inequalities that did not assume any cardinality constraint. So just some idea how this lifting works. I'll skip this in the interest of time. Another class of inequalities I talked about were the separation inequalities when all weights are equal. We are not in that case. We have at least two different weights. So we're going to restrict our set B to be those items that have the equal weight. So when we have two weights, they can be lower or higher. I'll call that AL and AH, the lower weighted and higher weighted items. Restrict your B to be, let's say, the lower weighted items. Write the lower weighted item separation inequalities and then lift them. Again, we can do this in closed form. No need to solve sequence dependence lifting problems, mixed integer programs, and these are also as strong as you would want them to be. So again, all of this is thanks to the submodularity. So again, this is very difficult in general, but we are able to do this for submodular functions of this particular form. restricting ourselves to two weighted items, how close are we to get to convex hull? So it turns out all these lifted inequalities that I talked about, in addition to one more inequality we call the super average inequality, are enough to give the convex hull of this set. Again, we took a nonlinear sort of concave submodular problem, and we were able to turn this into these linear programs. So if you just have the cardinality constraint, this is a mixed integer, linear program. If you have additional constraint, add those additional constraints, and this will be a mixed integer program. And separation is easy as well. Okay, so that was restricted with two distinct item weights. But if you have more than two item weights, we can use the inequalities that we had and sort of create new inequalities. Now I'm not going to talk about the convex hull anymore. I'm just going to talk about valid inequalities that are easy to generate. And these are going to be useful in my computational study. So one idea is to select two weights. You always have to select the lowest one. The yellow one is the lowest weight. A little higher is blue, red, and green. Let's think about it in that order. So you can now turn this problem, relax this problem into a two-weighted problem if you select, let's say, the yellow weight always, and one more weight, either the highest or the lowest, etc. Relax the problem, write the valid inequalities, and this will still be valid as long as f is monotone. So this is the case when f is monotone. For the more general case, we have an approximate lifting function for these inequalities as well. And I'll spare the details, but they're, again, in some sort of marginal contributions of adding item I to a subset Ti. So you can see f of Ti plus Ai minus f of Ti. That's marginal of adding item I or weight I to the subset Ti. And we have some valid inequalities. These are in linear format and easy to separate and add. So for the computational study, let's go back to that portfolio management problem, but let's make it realistic now that, now we do have correlations. So now I don't just simply have x transpose A in the square root function, which would have had assumed no correlations between stocks. So now I have in the risk term omega times square root of x transpose qx, where q is the covariance matrix of this portfolio. So q is a positive semi-definite covariance matrix, so it's not diagonal. I can do the nice simplification. So it's not in the form that I want, concave plus composed with a linear function. It's not submodular also in general, and this is an NP-hard problem in the cardinality constraint case. So how am I going to use submodularity? It looks similar to what I started out from. It's not quite there. So we apply a trick. So what I call here is the hidden submodularity. So there's some submodularity hidden in here somewhere. And it comes up like as follows. I'll take the Q matrix and divide it into two parts. R, a diagonal part, diagonal of with entries in A, a vector A, as well as the remainder R. So I'll write Q as a summation of R and a diagonal. And then I'll substitute that in that square root function. I'll divide that into two parts. The W part, that's going to capture the ax squared is A. Remember that x is binary, so x squared is equal to x. So that part can be simplified as the form that I want. That red form that you see is the form I'm familiar with, and that's submodular. And then the remainder, y, will be captured by the y variable. I'm going to keep that as is. And then z, the function that captures the the risk, that's multiplied by omega in the objective, while z squared is going to w squared y squared plus y squared. That's a second order conic function that the solvers today recognize and can deal with. So that's something that we can deal with. And then the cardinality constraint binary variables, and so on. So this is something that the solvers will accept. This will be my baseline comparison without exploiting submodularity. And then I will compare this formulation that I can enter to Gurobi already, which is the sort of the state-of-the-art solver that can handle this, with adding the inequalities that I've been talking about. So here is some sort of summary of our computations. So each row is the average of 5 trials. We have a time limit of 1 hour. When you see in the time column some superscript, those are the number of instances that did not solve to optimality within an hour, and some statistics about how we generated the data. Beta is our risk aversion parameter, the probability of being lower risk than the value at risk at beta. So we want that beta to be high. And we're comparing 3 methods. The top one, BC, so branch and cut, because we need to keep the integrality restrictions. This is the MP hard version. Lifted, extended polymetric rate, lifted separation, so that's what we propose. There was the closed form approximate lifted inequalities that I talked about, which was done earlier in the literature by you and Ahmed. And SOCP is the formulation that I showed you, but did not enhance with any valid inequalities that exploit submodularity. So the statistics that we look for, we look at the solution time, we look at the N gap, so if we hit the time limit, how far off are we from optimal, number of nodes in the branch and boundary, and number of cuts. If you're adding cuts, how many cuts that we're adding. So as you can see, for all these instances, and we have a lot more instances in the accompanying paper, I have only the summary here, but for these instances, for example, the original formulation that does not exploit submodularity, that's SOCP. For the easier instances, lower beta, it's fine. It solves within the time limit most of the time, except 3 of the 5 instances hit the time limit. And it explores many nodes, 70,000 nodes. As you go down, the complexity of the problem increases, and you can see when you have if you want to have high probability of high risk aversion, let's say, then none of these problems can be solved to optimality. Very large optimality gaps, 26.8%, lots of nodes explored. Whereas with these strong cuts, the strongest possible cuts in certain settings, add much fewer inequalities than the approximated cuts, and we're able to solve these problems relatively fast. So the fastest method, all instances for us solve within the time limit, so 0% gap. And in much fewer nodes with fewer inequalities. So this is what we like to see. And this is one way you can see the benefit of exploiting submodularity. So it may not be apparent again, but if you sort of catch it or if you uncover it, it might be to your advantage in terms of solving these problems as just linear programs. So this was one example when I could enter the f function to Gurobi, but again, for general functions, we don't even always enter these into solvers in an easy way. So that was the first part of my talk, sort of usual submodular function, but with additional properties of this concave composed with linear. So in my title, I talk about generalized submodularity. So this is something we think about. So a lot of the literature in submodular optimization is about set functions, whether to choose an item or not. So that's a binary sort of function, and we're interested in selecting one subset. So, and that subset means all the items in the ground set are homogeneous, they're interchangeable, so you're sort of trying to choose one subset out of this ground set. So that's classical submodular set function. One extension that we were interested in is this multi-set extension. So in the sensor placement, I have some data and computations that I will talk about. There are multiple types of sensors. So sensors might be measuring temperature, humidity, and light. So now I'm trying to select 3 subsets. Where should I look at my light sensors? Where should I look at my humidity sensors, etc.? So that's the multi-set extension of submodularity. And another extension we looked at is the mixed integer extension. So people have looked at continuous submodular functions, where now that x variable that I restricted to be binary is actually a continuous variable. You can think of these as energy levels, so a continuous selection of your energy levels in your sensors. So that would be a continuous variable. Or you could think of installing multiple copies of the same sensor type, and that would be the general integer extension. So these are relatively new. They have been looked at again in the approximation algorithms or continuous optimization settings, but they have not been looked at in the mixed integer programming sort of viewpoint that I've been following even for the classical submodular optimization that have been beneficial. So these are the two extensions we talked about in our tutorial paper. Today, in the interest of time, I'm going to stick with the multi-set extension, but it's really very interesting to look at these mixed integer extensions where we, again, take a very non-convex, non-concave function, and we are able to exactly characterize these with mixed integer linear programs with linear constraints. So start with the multi-set extension. I'm keeping an eye out on time. I'm sort of getting there, I think 3:15 with some time for questions. Yeah. All right, so let's talk about the multi-set. So again, if you want to think about where the submodular functions and generalized submodular optimization fits, classical submodular set function optimization and these multi-set mixed integer extensions are a superset, and in general, mixed integer nonlinear programming is a superset of this. So we're looking at very specific mixed integer nonlinear functions here. All right, so this multi-set functions, they have a name. So when you think about K subsets, selecting K subsets from a ground set N, that's known as a K submodular optimization. So that's the multi-set extension of submodularity. And the mixed integer extension that we've looked at, and there are some others as well, that's known as diminishing return submodular optimization. This is the part I'll skip in my talk, but it's available in our tutorial paper as well as an accompanying full version paper. Okay, so K submodular maximization. Again, now instead of selecting one subset from our ground set, we're interested in selecting K subsets, K disjoint subsets, because of the heterogeneity of the items that we're, or the sensors, let's say, that we're selecting. So type 1 sensors, type 2 sensors, type 3 sensors. So now we want to select 3 distinct subsets and evaluate their, let's say, coverage function F as a multi-set function. So instead of a single set function, we have a multi-set function. So now we'll be talking about K tuples of pairwise disjoint subsets of N. The notation K plus 1N will be the whole collection of all K subsets. So the K submodular function definition is a very natural extension of the submodular function definition that I gave you. Now, bold X is going to be this K sets. Bold Y is also the K set Y. And f of x plus f of y greater equal to f of x intersection, now in the multi-set sense, and union. And the multi-set intersection is what you would expect. Now in union, we have to be careful because of the disjointness of the requirement for these sets to be disjoint. So you sort of take out some items that might appear in other sets when you take the union. So naturally extends the usual submodular functions in terms of multi-type sensor placement. A coupled feature selection from machine learning has been studied by other authors and been recognized as a so-called bi-submodular function if you have 2 features that you're trying to select. There's a problem in healthcare, drug-drug interaction detection problem that has been shown to have the likelihood function of drug-drug interaction have been shown to be a K-submodular function, in this case bi-submodular function. And multi-topic influence propagation, again, in social networks. So all of these have been looked at and shown to be bi-submodular or K-submodular, depending on the number of subsets you're looking at. So in the, again, sensor placement setting, this is the building that we have, smart building. We're trying to install multiple types of sensors, and we want to locate each type, and we want to decide where to locate them. So blue is one type, and orange is another type. Where to locate which type of sensor. How do we measure how well we are doing with our sensor placement? There's a function, entropy function, that characterizes how well we're doing. I wrote down the mathematical form. It's complicated. It has logarithmic terms and so on. And then, it captures the unpredictability of the nature that we're trying to predict. And this entropy function that is highly nonlinear, non-convex, has been shown to be k-submodular in earlier studies. Again, I won't go into the details, just to show you that it's not a very nice function that you can enter easily. We want to maximize coverage, maximize entropy. We want to identify as much of the unpredictability as possible. Again, NP-hard problem. These are very hard to approximate as well, and the approximation ratios are often not very satisfactory, so 1/2 approximation. So these algorithms could give 50% of the optimal. And again, we're interested in exact methods. We were interested in being able to add additional constraints that can be written in linear form. Again, just a summary or the highlights. We are able to characterize valid linear inequalities. We can write these problems as mixed integer programs and write linear constraints to capture these highly nonlinear functions, hypograph in this case. Based on that, we can give an exact algorithm that is not your sort of brain dead, let's do an exhaustive search, look at all possibilities and choose the best option. And we show this in a multi-type sensor placement problem that we use data from Berkeley Intel Lab, that they have, again, light, humidity, and temperature measurements, and how to use that data to come up with the best sensor placement. The minimization version, very interestingly, in the bi-submodular case, k equals 2 case, it turns out to be polynomial time, and we are able to give the full convex L description for that case. And the minimization for k greater than or equal to 3 is an open problem, whether that is polynomial or not. So I'll stick with the maximization version again. The minimization version can be found in the paper. We'll do the same trick now you're familiar. For the k-set maximization, I'm going to just create copies of my variables, vectors, x, x1 through xk. Naturally, the way you would expect, xij will be 1 if I'm putting sensor I to my jth subset. So that's sort of what you would expect. Xiq sum less than or equal to 1, that makes sure that we are not the sets that we're putting items to are disjoint. And again, so what we do is now our little x is k copies of our x from before, and we're going to have a 1 if we're putting an item into the first subset or the second subset and the third subset and so on. And again, we'll take this maximization function. We're going to look at the hypograph like we've done before. I'll call that TF. And we're going to try and turn that into a mixed integer linear program with any constraints. So calligraphic x is going to be any constraints that you might have, cardinality, budget, etc. We will need to describe similar sort of marginal contribution definitions. So now sigmas are, so rows are going to be rho qi, marginal contribution of adding item I to the qth subset. So as naturally as you would expect, the same kind of marginal definition, only in the multi-set setting. And then we will need these coefficients psi iq. That's going to capture what I had before. What if I take out an item that I had started out with in my subset S that I started with, or multi-set S that I started out with, and turn that variable off. So that's the last item, last term you see in the valid linear inequality that I show for the hypograph. So those are a little hard to obtain, but lower bounds suffice, and we're able to characterize those in closed form as well. So up here you see the classical submodular inequality that I showed you earlier in the first bullet. And the k-submodular inequality looks similar, but now we have to figure out additional terms and use the properties of the multiset function, disjointness. But again, we can write these in closed form. In the set of single set, our k-submodular inequalities naturally boil down to submodular inequalities, and then they generalize to multisets. So again, don't worry about the mathematical details. This is just to show that it's a natural extension of the classical submodular inequalities that consider multisets. So we are able to characterize those coefficients in a closed form in a sense that they will make the inequalities valid. We call those K-submodular inequalities. And we can pose now these problems as mixed integer linear programs. Again, we have exponentially many such inequalities, but we don't add them at once, and we do a delayed constraint generation algorithm. So again, we took a nonlinear optimization problem over K sets and turned it into a mixed binary linear program through this method, which is, again, desirable because these are now solvable with existing solvers. So again, we had data sets from Intel Berkeley Research Lab that contain multiple sensor type measurements. The objective function is that entropy function that I showed you, which is highly nonlinear, and we're not able to enter that into Gurobi, unlike my concave case when I could turn that into an SOCP. This one, I cannot enter it into the solvers. So my only benchmark is that exhaustive search that I talked about, the one that tries to enumerate all possibilities and pick the best. Otherwise, we don't have a benchmark, even an algorithm that could solve this exactly. So here's a summary of the results. Again, ES is going to be our benchmark, the exhaustive search. As you can see, and as you would expect, this algorithm is not going to solve in reasonable time. It can only enumerate very small instances. The moment you increase the size of the instances or your choices, it cannot even sort of complete the job of enumerating. Whereas using this kind of a cutting plane delayed cut generation approach and our powerful mixed integer linear programming solvers like Gurobi, we can solve these problems well within the time limit. The hardest problem still takes less than half an hour, which you see at the bottom. We add a lot of cuts, but we have very easy ways of generating them, so it's not too difficult to add them, and the number of branch and bound nodes are very reasonable. So, again, a problem that we didn't know how to solve exactly, we can turn into this sort of mixed integer linear programs. So that's been another sort of interesting generalization of submodularity. This is some sort of a second set of the same instances, but just to highlight, we took how much time does it take for a function evaluation? How long would we have to wait for exhaustive search to finish its search? It turns out like a simple back of the envelope calculation, it would take 13 years to reach optimality for you to do exhaustive search, whereas for that highlighted instance, whereas we solve it in less than 8 minutes. So again, exploiting some modularity for these functions that are hard to optimize exactly, benefits in terms of finding the exact solution for this class of problems. One last class of problems, and I know I have 15 minutes for questions, or I can stop here, or I can just give a gist of this problem. I'll let Doug and Ebru tell me how you want to proceed. I can wrap up also. 5 more minutes. Just a quick, gist of this. Yeah, totally. So just the gist of another class of problems we refer to as robust submodular. I think this is also a very interesting application. So the motivation for this problem came from problems in water distribution safety. So suppose we're given a water network and a contamination scenario, and we're trying to place sensors to detect this contamination. We have some detection time that a set of sensors S detect the contamination from source J. So let's think of contamination scenarios as contamination sources for simplicity. So that's TSJ. And beta JT is the penalty function that denotes the amount of damage caused by scenario J, the contamination scenario J at time T. So if you do nothing, and if you don't place any sensors, beta J infinity would be how much damage it will cause, how many nodes it will reach, this contaminated source reaches. And if you interfere and place sensors and you detect it on time, we assume we can treat immediately. That will be beta J TSJ, and then the penalty reduction function RG is the difference between these two. No sensors, you let this disseminate through the water network versus you place the sensors, you detect in time, treat it, and you save some contamination. So that penalty reduction is known to be a submodular function. But given that we have multiple scenarios, and this is a case where we need to care about robustness, the worst case. What is the worst case? What is the worst amount of damage that can be caused? So here's an example. There's a contamination in node 1. The arc lengths give you how many hours it will take for it to reach the next arc that it's connected to. So if you do nothing in 2 hours, it's going to contaminate 3 as well, and you will have contaminated 2 nodes. Whereas if you place the sensors on those double circles, 1 and 2, let's say, well, 1 will detect the contamination immediately, treat it, and then there will be no dissemination of this contamination, and you will have saved 2 nodes. So that's the penalty reduction function that is submodular. Again, it has this nice property. I have another scenario. I'll skip that in the interest of time. So the robust submodular function maximization, so we're trying to look at the worst case damage and minimizing that damage. So it can be written in this form: max x and x, min I and m, some scenario functions, fix. For each scenario, we have this function of contamination and penalty reduction, divided by alpha I to capture multiple problems that have been looked at. So alpha equals 1, so no denominator has been studied in the literature, as well as alpha equals to max x and fix. What is the best you would have done if that was the scenario that you were looking at in terms of maximizing penalty reduction? Again, it's NP hard to approximate. Objective function, the inner objective function that we're trying to maximize is not even submodular. Minimum of multiple submodular functions is not necessarily submodular. But can we still exploit the submodularity of each fi? It turns out if you write this, if you sort of rewrite it, introduce the function eta is less than or equal to theta I, alpha I, theta is less than or equal to fix. This red function now becomes a hypograph of a submodular function, and now I can use the inequalities that we know, strengthened or original submodular inequalities, to now solve this as a mixed integer linear program. Some practical considerations: adding 1 submodular inequality time for each function results in many inequalities. That's going to be our benchmark. We show some properties of what inequalities to add, which ones are strong, so some computational enhancements of what we can do. And we can show when they're facet defining, when they're the strongest possible, which ones to avoid and which ones to add. So that's a short summary. And long story short, again, compared to a baseline algorithm of adding any inequality that you see, and again, this function is hard to compute, so we want to do this delayed constraint generation algorithm. The baseline algorithm, again, 3 replications, oftentimes hit time limit and not able to solve, not able to even give us a gap or a solution. Now we can solve with our proposed method of enhanced sort of submodular inequalities for this robust submodular maximization problem. So I did rush this a little bit, but we use data sets from US Environmental Protection Agency, as well as Battle of Water sensor network problems that are commonly used in these water contamination detection problems. So quickly, submodularity also arises in a class of problems called chance constraint programming. I'll skip the details of this, but if you look at a chance constraint problem with right-hand side uncertainty, this is a well-studied problem, and a class of inequalities called mixing inequalities were proposed for this problem. What we observe is the function that you're looking at when you're writing the mixing inequalities for chance constraint programming is nothing but a submodular function, and the inequalities that we know are nothing but extended polymatroid inequalities. Other observations, even distribution robust chance constraints, this is a very popular topic right now, and if you write a mixed integer linear programming formulation of this, it also has the submodularity structure that can be exploited. Especially if your decision variables are pure binary, there's even more benefit you can get by exploiting submodularity. Interestingly, there are scenario reduction problems in stochastic programming that have been looked at. And this also has a submodularity property. If you have 100 scenarios to describe your uncertainty in discrete settings, adding one more scenario gives you more information than if you had 1,000 scenarios and if you had one more scenario. So it sort of appears everywhere. I find them to be very fascinating. Everywhere I look, I started seeing submodularity. So hopefully I was able to convince you that there are some problems that you might find interesting and that have this property. Sometimes it's hidden and you have to sort of dig it out. But if you can find it and you can use it computationally, you would benefit, and you would turn these nonlinear, non-convex looking problems into mixed integer linear programs if you follow this strategy. So I'll end there and answer any questions that you might have.
So for the portfolio problem, you do this kind of Markowitz formulation, and then you say it's equivalent to var, right? So I was wondering if you can do CVAR or some other risk measure, but maybe you can because distributionally robust and coherent risk measures are kind of the same thing.
Yeah, I mean, CVAR, you have a good point. So CVAR with the discrete setting has a linear programming sort of representation. So that's convex, that's nice. Yeah. So I may not have the linear functions are submodular, but I may not benefit much from submodularity in that setting.
Well, you have integer, I guess. But for general coherent risk measures, could you do something with this?
Yeah, I mean, one will have to, so this is one trick, is that you will have to look at the function you're interested in and make sure that that is submodular. So, we will have to think about whether the coherent function of interest is submodular, but that would be the trick. Yes.
Thank you for a great talk. My question would be, I know that you skipped it for the interest of time, but could you give some comments on whether we could use the DCG for minimization of DR or alpha weakly DR submodular optimization problems, please?
Yes, so for DR submodular, the diminishing return submodular, we have a paper that is under review that we can actually, it is the first time we are able to establish that class of problems are polynomially solvable because we are able to give the convex hull. So the minimization of DR functions in the mixed integer setting also, surprisingly, we are able to give even under certain constraint types. And your second question was alpha submodular. Yeah. That's something we haven't looked at. So we're looking at sort of generalization of submodular functions. We are now looking at L convexity and natural convexity, but alpha submodularity is something we haven't looked at yet, and there might be opportunities there that I haven't thought about yet, but good question.
Yeah, thank you. Yeah, I might be greedy because that's the problem I'm solving, and knowing that, we can try this mixed integer program would have been very cool.
It may be possible. I'm not sure as yet. Yuri.
Thank you for your talk. So I was curious about the definition of union in the case of modularity. So it seems to me that either you make it order dependent, or you have to kick out an element that is in multiple sets.
It is not order dependent.
So if an element is in more than one of the sets,
you discard it all.
Which is a little strange, no?
Yeah. Yeah, but it is one. That is the definition of K submodularity. There are other definitions also. So multi-modular.
So I was wondering if the fractional definition comes from the fact that if an item appears multiple times, then maybe you want to split it among the set.
That could be a motivational looking at a fractional version. That's a good question. Yeah, so it's very interesting that there are various generalizations of submodularity that appears in, let's say, the CS type literature. And the K submodularity, you're right, you take it out from an element out from all sets, but if you did a fraction, that will be a multi-set mixed integer. We haven't combined the two. I think it may be possible to combine the two, but that would be one motivation, I would think. That's a good question.
Well, again, we have to thank our speaker.
Thank you. Thank you for coming.